Hi, Jim Frankenfield here with another academic video. This is a problem solution, not a lesson video. And the problem I'm going to solve in this video is to graph a rational function. So let's take a look at that. It's a real beast of an expression here, but we're just going to follow the usual procedure for this. And the function we're going to graph looks like this. We've got some pretty large factors to find here, or large numbers to find the factors for. We're going to want the factors and roots of the bottom. So we're going to want to start by finding the prime factors of 330 and then use those to find the factors of the polynomial. And we're going to do the same thing in the numerator, except that we can already reduce this. You can factor a 3 out of the top. And you can tell that because you have a 3 here. 7 plus 5 is 12. That divides by 3. This is sum up the digits is 6. That divides by 3. 12 divides by 3. And 18 divides by 3. So if you add up the digits and they divide evenly by 3, the number divides by 3. Pretty cool little rule. So instead of 8190, if I take the 3 out, and I'm not going to rewrite it, but if we divide it by 3, we're going to have 2730. So I need the factors of that. So I need to find first the prime factors of 330 and the prime factors of 2730. So I'm just going to go ahead and do this, and then I'll fast forward it in the video. And we're just going to go into kind of algorithm mode here and do this the way I usually do this. I do have another video on prime numbers, including factoring them. So let's just go ahead and do that. Okay, so now we have the prime factors of the numerator and the denominator. Oh, this is the denominator. I'm going to use those to find the factors of the polynomial, and I have another video on this also. Let's begin with the denominator. And what I'm going to do is just use a spreadsheet, and I'm going to create a spreadsheet with all the possible combinations of the prime factors, and that gives me all of the possible factors, which may or may not be prime. So I'm just using the spreadsheet here, and here's my 2, 3, 5, 11, and I'm taking every combination of those prime factors to find every possible factor. So remember that the rational roots theorem tells us that the roots need to be rational, if they're rational, need to be a factor of the trailing constant. And these are all factors of 330 now. And then I just evaluate the function. That's the function, the denominator function. And I see if I get 0. And I get 0 here, 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 and here. So I listed them over here in this column. So these are the 4 roots of the denominator. Minus 11, minus 3, minus 2, and 5. Oh, this should be a plus 2. I don't know why that's not plus. Okay, if we had to do this by hand, this would be pretty terrible one to have to do by hand. We could try to reduce it by Descartes' rule. Sometimes that helps us choose our first numbers. Sometimes it might eliminate all negatives or all positives. If we did look at that just for review, I have in the denominator how many sign changes. Plus, plus, there's one sign change. There's a second sign change. So there's 2 positive and 2 negative, assuming there are no imaginary roots. And this kind of problem, well, sometimes it might have imaginary roots. we often create them so that they don't. So those are the denominator factors. So I did the same thing on the numerator. Here are my factors, 2, 3, 5, 7, 13. These are the factors, and then I think this has been sorted after doing it so that all of the roots are at the top. This has been sitting around in an open tab on the browser and sitting around on my desk for a while we were moving. This is a new place and a new studio, in a new office. And hopefully I'll be improving my studio here a bit and my teaching and tutoring tools, especially for teaching. I've been tutoring. I'm hoping to expand very soon into actually teaching, which requires different tools and a different approach. Anyway, these are the factors of the numerator. We have 5, 7, 13, and -6. So let's go back and look at these. The 5 means that there's a factor of x minus 5 in the denominator, and there's also an x minus 5 in the numerator, which means that those will cancel, except I have to make a note that x is unequal to 5. I'm going to end up with a hole there. Okay. Because they cancel, the function will go through that point smoothly, but it won't exist at that point. So it's important to make a note of that when we graph this. The other denominator factors will give us vertical asymptotes. The function won't be defined there, and it won't cancel either. So we'll have a vertical asymptote, and it won't be in the domain. Where it's 0 in the numerator, we're going to have zeros where we cross the x-axis. This is where y will equal 0. So we have almost all the information that we need. Let's look at what happens when x approaches infinity, plus or minus infinity. Well, the terms the lower order below x to the 4th won't matter. The bigger you get, the less these matter. So I'm going to end up with 3x to the 4th over x to the 4th, or y is going to get pretty close to 3. So y equals 3 is going to be a horizontal asymptote. So let's start putting these things together on the graph. And okay, so I have this set up in Desmos now here, all ready to go. The denominator roots were -11, -3, and +2. And it's a little faint, but you can see the dashed blue vertical asymptotes. We're going to have to approach those vertically. The numerator gave us the zeros, and that gave me 7, 13, and -6. So those are points that are zeros, so I can put those on my graph now. I could be doing this by hand the way we used to do it, but I set it up in advance to make it look a lot neater here. We know that y equals 3 is a horizontal asymptote. So we could kind of start to fill this in. We know up here in the upper left that it's going to approach the horizontal asymptote and the vertical asymptote, and there's no zeros over there, so it's going to be up here in the upper part. The other ones you can sort of take a guess here, but let's see, we have, sometimes you need to fill in a point, but the other thing you can do is just because you're approaching 3 doesn't mean you don't cross 3. So let's see whether we cross the horizontal asymptote. And to do that, we have to set our whole original function equal to 3. And you can carry that out, it would be rather tedious. Yeah, I put it over here. If you do this in symbolab, or if you do it by hand, you hopefully get the same thing. there's 2 points where I cross the horizontal asymptote. At these values of x, y is going to equal 3. So this is another often useful thing to do, although sometimes it's more worthwhile than other times. It can sometimes be a little too tedious. So we have these 2 points. And the last thing that's easy to get is what happens when x is 0. Well, when x is 0, I'll go back to my function in Desmos here. I'm going to have minus 8190 over 330, and that turns out to be about minus 24.82. So we have another point. So we filled in a lot of logical points, and we have all the asymptotes, and we're ready to fill this in. I can see that up here in upper left, it's going to have to come down and go over to the left and approach the 2 asymptotes. In the center, there's 1, 0, 1 point above it, and it's in between 2 asymptotes. So it's going to have to go down to the left one and up to the right one. This other section in here has a point down here, and if it opens, if it's sort of parabola shaped, if it opens upward, it'll have to cross the x-axis, and there aren't any zeros there, so it can't do that. So this is going to have to go open downward, and this will be well, I don't know if it's the high point. High point's probably somewhere near there. Some fine points you have to just either calculate the point or fill in some more detailed points. But a lot of times we want to get the general sketch and the key features, which is what we now have. We have to approach this asymptote. We have to go through this point and these 2 zeros. So I'm guessing this is going to come down and go through here and approach this. It couldn't really come up and go through this point and then come back down if it crossed the horizontal asymptote. It could touch it once, but I believe it's going to go through it once. I don't have anything that would indicate it would turn around at that point. So it's going to come back down and go through these. So I could fill that in if I was doing it on paper now. And let's see, here we go. This is what we were able to surmise from following our procedure and finding the asymptotes. There's 3 vertical asymptotes we could find easily. We could find the zeros easily, relatively easily, if you find the factors of the polynomial. We found these 2 points using symbolab. It would be a little more complicated by hand, and that depends on the problem, but they're useful points to check. You may or may not cross your horizontal asymptote. Some functions will approach that without ever crossing it. Others will cross it. Unlike a vertical asymptote, which is never crossed because it's not in the domain, there's no value there, the horizontal asymptote can be crossed, and so could an oblique one if you had that. And we figured out that this had to go down to the left and up to the right. This probably is the actual maximum based on what this is telling me here. Desmos would show me the maximum value, and it's showing me the 0 point, so it could be slightly off the maximum, but it doesn't look like it is. That's the kind of thing we'd have to do some further analysis with. And over here, as we expected, it comes down through the horizontal asymptote, 2 zeros, and then it approaches the horizontal asymptote. So I zoom out, you can see how it approaches all of those asymptotes. One other point is that what happened to 5? X was equal to 5. Let's zoom in on that. There, undefined. So Desmos will tell you it's undefined, and when you hover over it, there's a little open circle, which is usually what we use to denote this kind of missing piece of the domain. It's just a missing item in the domain, really. It won't show you that until you zoom in on it. If you wanted to do this on Desmos and hand it in as an assignment or something, you could create your own point that's more or less there, and you can make it an open circle. So now I have my open circle, but I had to add that, otherwise it will only show up when you hover over it. So there we have our function. We started out by finding the, you notice when I factored a 3 out of the top, but it was never necessary to go and rewrite that. It's maybe a nice thing to do, and you might have to in an assignment, but it's not really necessary. I never had to do that. I just factored a 3 out in the front, and these will be whatever they are divided by 3. I found the factors, the prime factors of this one, and the prime factors of this one. That means when I'm looking for factors that I could have a plus factor or a minus factor. So if the factors of 330 could include any combination of the prime factors. And that's where we went to the spreadsheet. And of course, these days you would just factor it on symbolab or something. But this is one more analytical way to do it. And we set up a spreadsheet with the prime factors. And this is the topic of one of my earliest videos. These are all the factors. Over here is just a minus sign. So if 11 is a factor, minus 11 is a factor. Remember, plus and minus are both possible factors. And then I just test them out to see if I get 0. And this is a lot easier than trial and error by hand, although it's not as simple as putting it into symbolab. I did the same thing on the numerator, although this was sorted later so that all of the zeros at the top, so you won't see the pattern in the area over here. But that's how I found the factors, or the, not the prime factors, but the actual factors of the function. So I listed those down here. In this case, they were prime factors, but some were negative and some were positive. Over here, I had a factor of 6, which includes the 2 and the 3, and that was negative. Then I just went ahead and used these things to graph my asymptotes and my zeros. I considered what happens and since the power, since the order of the polynomial is 4 in both the top and the bottom, I can just look at the coefficient and I can see that it's going to approach 3. So that gave me a horizontal asymptote. And I remember I canceled a 5. I noticed that I had a 5 in both places. And then I put in 0. So I calculated f of 0, which is just this divided by this, and that gave me another point. And then something that I often try to do, if it's not too bad, is to find out if I cross the horizontal asymptote and where. And in this case, we had a couple crossings. So that gave us everything we needed to fill in the graph. And at that point, you can sketch the graph. And the goal is usually, this isn't precise at every point. If I do it by hand, it is on Desmos, but it wouldn't be by hand. But in an assignment or an exam, what we're usually looking for from students is to have the main features. I would expect a student to have the vertical asymptotes, the horizontal asymptote, the right shape in each of the regions, the zeros, this point down here. I wouldn't necessarily expect them to find this, but sometimes it's a good idea. You may or may not be expected to do that. And then you'd be able to fill in the shape of the graph. And that's the goal traditionally. And now that we can use something like Desmos, it actually is precise. But I could have sketched this by hand, and it wouldn't be precise at all the points, but I would have the shape right. I would know what the function looked like. So that's an example of a graphing a rational function. We also used prime prime factors. So we had to find the prime factors and have a video on prime numbers and prime factors. But if you're doing this kind of problem, hopefully you know how to find the prime factors. I used the prime factors in a spreadsheet to find the roots of the two polynomials. There are different, you can do it by trial and error, by trying every possible factor by hand. You still have to identify every possible one. There is a video or two where I describe and use the on factoring, and I use this method. Those were early videos. I was going to re-record one and haven't. I think there may be an error because I was paying attention to a crappy webcam more than my content. But we found the roots that way, and then we put all that together. We found 1 point at x equals 0. We found the whole, and so we used a bunch of different math. And I recently had somebody, a parent of a grade 7 student, wanted to know when he could take AP Calculus. And I had to explain that it's going to take a few more years. You can see that math is pretty cumulative here. You can't just jump into this, and you need to be able to do this before you get into calculus. You can't jump into this until you know how to factor these things and understand asymptotes and poles and all that. And we needed to understand prime factors and factorization in order to do that. So if you're up to this point, that's great. I hope you have all the prerequisites we used here. And if you're continuing on, I hope you'll get this material down well enough to move on. This would probably be either college algebra or pre-calculus. They overlap a bit. That's it, and I'll see you next time. Bye.